Right now, at this moment, something is passing through you. It has no color. It carries almost no energy. You cannot feel it, and no instrument in your daily life would register it. But it is real, and it is ancient, and it is everywhere, filling every cubic centimeter of space, streaming through walls, through atmosphere, through the soft tissue of your body without pause or interruption. It is light, or rather, it was light, long ago, in conditions so extreme that the word light barely captures what it was. Now, it has cooled, stretched, and quieted into microwave radiation. Astronomers call it the cosmic microwave background, and if you know how to read it, it contains, written in temperature fluctuations smaller than 100,000th of a degree, the earliest legible record of our universe. That record, when translated through a century of physics, through telescopes and satellites and equations refined across generations, tells us something precise and astonishing, that the universe we inhabit is approximately 13.8 billion years old. That number is not a guess. It is not mythology. It is a measurement, or more precisely, it is an inference, constructed from interlocking lines of evidence, each independent, each pointing to the same answer. How we arrived at that number, what it actually means, and where the certainty ends, that is the story we are about to follow. It begins not with the beginning of time, but with the light that survived it. There is a particular kind of knowledge that takes patience to appreciate. It is not the knowledge of revelation, not the sudden flash of insight or the dramatic discovery. It is the knowledge of accumulation, the kind that builds slowly, through disagreement and revision, through instruments pointed at the same patch of sky from different angles across decades. The kind where confidence arrives, not as a shout, but as a quiet convergence. Modern cosmology, the science of the universe's origin, structure, and age, is precisely that kind of knowledge. It is not complete. It has edges. It rests in places, on assumptions that are well supported but not proven in the deepest sense. But within its domain, within the range where our instruments and equations hold, it is among the most precisely verified bodies of knowledge ever assembled. To understand what 13.8 billion years means, we have to understand what kind of thing it is. It is not a number carved into reality. It is a derived quantity, extracted from a model, tested against multiple forms of evidence, consistent across independent methods. The number depends on assumptions about how the universe is structured, what it contains, and how those contents interact. Change the assumptions and the number shifts. Not dramatically. The evidence is tight enough to constrain the answer within a narrow range. But it shifts. That dependence matters. It is not a flaw in the science. It is the honest nature of how cosmological inference works. We will return to that dependence more than once, because the 13.8 billion year figure is genuinely extraordinary, and understanding it means understanding both its precision and its foundations. Let us start with what we can see. Look out at the night sky, and you are already looking into the past. Light travels at a finite speed, approximately 300,000 kilometers per second. The light arriving at your eye from a star, 100 light years away, left that star 100 years ago. The star you are seeing is the star as it was, not as it is. Distance in space is also distance in time. This is not metaphor. It is geometry. Scale this up, and the consequences become vast. Galaxies millions of light years away are seen as they were millions of years in the past. Galaxies billions of light years away are seen as they existed in the early universe, when structures were younger, smaller, less evolved. The deeper we look, the further back we see. The universe provides its own archive, written in light, organized by distance. In the 1920s, astronomers began noticing something systematic in the light arriving from distant galaxies. The spectral lines, the fingerprints of specific elements encoded in light, were shifted toward the red end of the spectrum. Not randomly. Not in different directions for different galaxies. Systematically, with the shift proportional to distance. The astronomer Edwin Hubble, building on earlier observations and theoretical work, quantified this relationship. The further a galaxy, the faster it appeared to be receding. This relationship, known today as the Hubble-Lemaître law, in recognition of the Belgian priest and physicist Georges Lemaître, who derived it theoretically before Hubble's observational confirmation, implied something radical. The universe is expanding. Not expanding into something. Not galaxies flying through a fixed background. Space itself, the fabric between galaxies, is stretching. The redshift we observe is not a Doppler shift in the traditional sense. It is the stretching of light waves as the space they travel through expands. The universe is not a static container. It is a dynamic geometry. This single observation, that distant galaxies are receding at velocities proportional to their distance, is the foundation of modern cosmology. Everything else builds from it. If space is expanding now, then it was smaller in the past. Run the expansion backward, like rewinding a film, and the universe contracts. Galaxies converge. Space grows denser and hotter. Wind the clock back far enough, and the universe reaches states of unimaginable compression. Temperatures and densities so extreme that atoms cannot hold together. That matter as we know it dissolves into its components. That even the components break down into a hot, undifferentiated plasma. This is the picture implied by expansion. Not a moment of creation in a theological sense. Physics has nothing to say about that, but a moment, or more precisely an epoch, at which the universe was in an extraordinarily hot, dense, nearly uniform state. This picture was proposed and developed through the mid-20th century. It was controversial. Some physicists found it uncomfortable, too suggestive of a moment of origin, too close to cosmological mythology. The term Big Bang, coined by the astronomer Fred Hoyle as a dismissal, became the model's name. The dismissal did not last. The model made predictions, and one of those predictions, made precisely in the 1940s by George Gamow and his collaborators, was tested and confirmed in a way that changed cosmology permanently. If the early universe was as hot and dense as the model predicted, then in the first minutes after the hot early state, nuclear fusion would have occurred under specific conditions. The universe would have been hot enough to fuse protons and neutrons into light nuclei. But it would have also been cooling fast enough to shut fusion down before heavier elements formed. The model predicted specific ratios, roughly 75% hydrogen, 25% helium-4, with trace amounts of deuterium, helium-3, and lithium-7. These are not rough estimates. They are calculated predictions derived from known nuclear physics applied to the conditions the model specifies. And when astronomers measure the primordial abundances of these elements, looking at regions of the universe that have not been processed through stars, where the original composition is preserved, they find agreement, not approximate agreement. Agreement within the uncertainties of the measurements, the ratios match. This process, Big Bang nucleosynthesis, is one of the most powerful confirmations that the hot, early universe was real, not inferred, not hypothetical. The elements exist in the proportions the model predicted. That prediction was made decades before many of the confirming measurements were taken. That is the kind of evidence that earns confidence. But the most direct observational evidence for the hot, early universe came not from element ratios. It came from the sky itself. In 1965, two radio engineers at Bell Telephone Laboratories in New Jersey, Arno Penzias and Robert Wilson, were calibrating a large horn-shaped antenna. They kept detecting a persistent hiss of microwave radiation. It came from every direction equally. They could not eliminate it. They checked their equipment. They removed pigeons that had nested in the antenna and cleaned away the residue. The noise remained. What they had found, without initially understanding it, was the echo of the hot, early universe. When the universe had cooled sufficiently, approximately 380,000 years into its history, electrons and protons combined to form neutral hydrogen atoms. Before that moment, the universe was a plasma. Electrons free, light constantly scattering, the universe effectively opaque. After that moment, the epoch called recombination, the universe became transparent. Light was released. It flooded outward in all directions. That light has been traveling ever since. As the universe expanded, the wavelengths of that light stretched, redshifted, from visible into infrared, then into microwave. Today, 13 billion years later, it fills the universe as a faint cold glow. Its temperature is 2.725 Kelvin, barely above absolute zero, and it arrives from every direction with almost perfect uniformity. That is the cosmic microwave background. That is what Penzias and Wilson had detected. They received the Nobel Prize. The universe had left a fingerprint on the sky, and we had found it. The uniformity of the CMB is not perfect, and that imperfection is, in a very real sense, the origin of everything we see around us. Across the sky, the temperature of the CMB varies by tiny amounts, fluctuations on the order of 100,000th of a degree. These are not noise. They are structure. They represent slight variations in the density of the early universe at the moment of recombination. Regions that were slightly denser, pulled in surrounding matter through gravity over billions of years, growing into the galaxies and galaxy clusters we observe today. Regions that were slightly less dense became the vast empty voids between structures. The pattern of these fluctuations has been mapped with extraordinary precision, most recently by the Planck satellite, which spent years surveying the full sky in microwave frequencies. The resulting map, a detailed image of the universe at 380,000 years, is among the most scientifically rich objects ever produced. Every peak and trough in the temperature pattern carries information about the contents of the early universe, the geometry of space, and the rate of expansion. From this map, cosmologists extract the parameters of the universe, the relative amounts of ordinary matter, and dark energy, the curvature of space, the amplitude of early density fluctuations, and through the Friedmann equations, the age. The Friedmann equations deserve a moment of attention because they are the engine of the age calculation. Derived from Albert Einstein's general relativity in the early 20th century by the Russian mathematician Alexander Friedmann. These equations describe how a universe filled with matter and energy evolves over time. They relate the rate of expansion to the contents of the universe. Put in what the universe is made of, the densities of matter, radiation, dark energy, and the equations tell you how fast it was expanding at any point in time, how fast it is expanding now, and therefore how long it has been expanding. To calculate the age, cosmologists integrate those equations backward from the present to the point where the equations break down. The earliest moment they can describe. The answer depends critically on what you put into the equations. Different compositions give different ages. This is where the model dependence lives. The 13.8 billion year answer is the answer that emerges when you feed in the composition measured by the Planck satellite within the framework of the standard cosmological model. That framework has a name, ΛCDM, lambda cold dark matter. Lambda refers to the cosmological constant, a term Einstein introduced, later abandoned, and which modern observations have forced back into the equations to account for the accelerating expansion of the universe. CDM refers to cold dark matter, a component that does not emit, absorb, or reflect light, but which has gravitational effects detectable throughout the cosmos. Together, these two mysterious components, dark energy and dark matter, account for approximately 95% of the total energy content of the universe. This is worth pausing on. The framework that gives us 13.8 billion years describes a universe in which the vast majority of what exists is unknown. Dark matter has never been directly detected as a particle. Dark energy has no identified physical mechanism. Their existence is inferred from gravitational effects, from the behavior of expansion, from the structure of the CMB. But their nature remains open. We are measuring the age of a universe we understand only partially, using a model built partly on components we cannot yet identify. That is not an indictment of the science. It is the honest status of the science. And the status deserves to be named. The convergence of evidence for 13.8 billion years does not come from a single measurement or a single method. It comes from multiple independent lines of inquiry that happen to agree. The CMB gives one value: the large-scale structure of the universe, the way galaxies cluster, and the characteristic scale of those clusters, known as baryon acoustic oscillations, provides an independent check. Type 1. A supernovae, which serve as standard candles for measuring cosmic distances, constrain the expansion history and point to the same approximate age. Globular clusters, ancient collections of stars whose ages can be estimated from stellar physics, set a lower bound. They must be younger than the universe, and their measured ages are consistent with a universe approximately 13.8 billion years old. 4 independent methods. Different instruments, different teams, different assumptions about different physical processes, all converging within a narrow range. That convergence is what produces confidence. Not certainty, confidence. There is a difference, and it matters. Certainty would mean the answer cannot change. Confidence means the answer is well supported by current evidence, consistent across multiple checks, and unlikely to shift dramatically. But it can shift. It has shifted before, modestly, as instruments improved and models were refined. And there is, at present, a specific tension that is actively shifting the conversation. In the 1990s, 2 independent teams of astronomers set out to measure the expansion of the universe using distant supernovae. What they found was not what they expected. The expansion was not slowing down, as the gravitational pull of matter should cause. It was speeding up. The universe, in the current epoch, is expanding faster and faster. Something was pushing space apart. They called it dark energy. Its discovery earned the 2011 Nobel Prize in Physics. The expansion rate today is described by a number called the Hubble constant, named in honor of the astronomer who first quantified expansion. It is usually written as h0 and expressed in units of kilometers per second per megaparsec. How fast space is expanding per unit distance. There are 2 primary ways to measure it. The first uses the early universe, the CMB, and baryon acoustic oscillations, to constrain the expansion history, then extrapolates forward, using the model to determine the current rate. The Planck satellite gives a value of approximately 67 kilometers per second per megaparsec. The second uses a chain of distance measurements in the late universe, calibrated using Cepheid variable stars, which pulse at rates related to their brightness, and type 1a supernovae, to measure expansion directly and locally. This late universe method consistently returns a value closer to 73 kilometers per second per megaparsec. 67 versus 73. Those numbers look close. They are not. The discrepancy is statistically significant. The disagreement exceeds 4 standard deviations, which in physics represents a serious anomaly. It has persisted as measurements have improved. It has survived multiple checks for systematic error. It has a name now: the Hubble tension. The Hubble tension does not overturn the 13.8 billion year figure dramatically, but it sits within the calculation. If the tension reflects a real discrepancy, not a measurement artifact, but a genuine incompatibility between early universe and late universe physics, then either the model needs modification, the measurements have undiagnosed errors, or there is physics operating in the early universe that we have not yet accounted for. Some proposals involve early dark energy, a component active before recombination that slightly altered the expansion history. Others point to modifications of gravity. None has yet achieved consensus. The tension is unresolved. This is living science, not crisis. The model remains extraordinarily successful across an enormous range of observations. But friction, the kind of productive friction that has historically preceded genuine advances. The 13.8 billion year figure sits within this friction, acknowledged and precisely understood, holding with confidence while the debate continues around it. we have traveled backward through time, from the present expansion to the CMB at 380,000 years, to Big Bang nucleosynthesis in the first minutes. Each step has moved us further from direct observation and deeper into inference. The element abundances are indirect evidence of conditions we cannot observe directly. The CMB marks the earliest moment from which light can reach us. A wall of plasma, before which the universe was opaque. Before 380,000 years, we cannot see, not because our telescopes are insufficient, though more powerful instruments would help at later epochs, but because the physics of the early universe prevents light from escaping. The observable universe, in the electromagnetic sense, begins at recombination. Everything earlier must be inferred from what that boundary preserves. And yet, we believe we understand, in broad strokes, what happened earlier. Because Big Bang nucleosynthesis gives us a window, however indirect, into the first minutes. Because the physics of plasma and radiation and nuclear interactions is well understood. Because the predictions made by applying that physics to early conditions match what we observe now. But as we push further back, the certainty shifts, not abruptly, but progressively. The further back in time, the higher the energies involved, the more our understanding depends on extrapolating known physics into regimes not yet directly tested. There is a particular epoch where this becomes acute. An epoch so early that the observable features of the universe, its flatness, its near uniformity, the specific pattern of its temperature fluctuations, are difficult to explain within the standard model of expansion alone. The universe, as we measure it, is geometrically flat to extraordinary precision. The sum of its angles in the sense of cosmic geometry is indistinguishable from exactly 180 degrees. Its temperature, as recorded in the CMB, is nearly identical in all directions, to a precision of 1 part in 100,000. And yet, in the standard picture of expansion alone, regions of the sky that are on opposite ends of what we can observe were never in causal contact. They were too far apart, even traveling at the speed of light, to have ever exchanged information. How did they reach the same temperature? And why is the universe so precisely flat? In the standard expansion, small deviations from flatness grow over time. A universe even slightly curved in its early history should by now be dramatically curved. We observe no such curvature. These are not mysteries invented for narrative convenience. They are real technical problems. Problems that the standard expansion model does not solve on its own. The leading proposed solution is cosmic inflation, a period of extraordinarily rapid, exponential expansion in the earliest moments of the universe, occurring before the universe was a fraction of a second old. In a period of inflation, a small causally connected region would have been stretched to enormous size, ironing out curvature, homogenizing temperature, producing a nearly flat, nearly uniform universe as its legacy. And quantum fluctuations during inflation, stretched to cosmological scales, would have seeded the tiny density variations that eventually became the structure we observe. Inflation is elegant. It solves multiple problems simultaneously. It makes predictions, a nearly scale-invariant spectrum of density fluctuations a specific statistical character to the CMB anisotropies that are consistent with what Planck observed. But inflation has not been directly confirmed. The inflationary epoch, if it occurred, happened at energies and timescales so extreme that no current or foreseeable instrument can observe it directly. The specific field that drove inflation, the inflaton, has not been identified. The most distinctive prediction of many inflationary models is a background of primordial gravitational waves, which would imprint a specific polarization pattern on the CMB, called B modes. Dedicated experiments have searched for this signal. It has not been found at detectable levels. Inflation is the best available explanation for what we observe. It is mathematically developed and physically motivated. But it remains an inference about an epoch we cannot directly access, driven by a mechanism we cannot yet identify. The distinction matters, not to dismiss inflation, but to hold it at its appropriate level of confidence. Push further back, past inflation's proposed epoch, into the first fractions of a second, into temperatures and densities that exceed anything physics has tested experimentally, into a regime where the ordinary tools of physics begin to diverge in ways that signal the limits of the theory rather than the limits of our knowledge alone. At a moment approximately 10 to the negative 43rd seconds after the hot early state, a duration almost incomprehensibly small, defined by fundamental constants as the Planck time, something specific happens to the equations. General relativity, the framework that describes gravity and the large-scale structure of space-time, predicts that at sufficiently extreme densities, curvature becomes infinite. The equations produce what mathematicians call a singularity, a point at which the mathematical description breaks down. But singularities in physics are not physical objects. They are signs. They signal that the theory being applied has exceeded its domain of validity. At the Planck scale, general relativity must be reconciled with quantum mechanics, the framework governing the behavior of matter and energy at small scales. These two frameworks, each extraordinarily successful within its own domain, are fundamentally incompatible at their foundations. No theory that unifies them has been verified. String theory, loop quantum gravity, and other proposals exist, each with mathematical structures and internal consistency, but none has made predictions that have been experimentally confirmed. The Planck boundary is therefore not a mystery in the dramatic sense. It is a horizon of method. It is the point at which our best tested theories lose their calculational footing, not because reality ends, but because our description of reality has reached its verified range. Beyond that boundary, or before it in the temporal sense, we do not yet have physics that holds. We do not yet know is a precise and honest statement. It is different from we will never know. It is different from anything is possible. It acknowledges a current limit without inflating that limit into permanent ignorance or collapsing it into false humility. The next advance in theoretical physics may extend our reach backward. It may not. What we can say is that our current tools, applied with integrity, stop here. There are proposals for what might lie before or beyond the Planck boundary. Cyclic models in which the universe passes through successive expansions and contractions. bouncing cosmologies, in which the hot early state was preceded by a collapsing phase, the ekpyrotic model derived from string theory, in which universes arise from the collision of higher dimensional structures called branes. These are serious theoretical proposals, developed with mathematical rigor by serious physicists. They are not mythology or speculation in the casual sense, but they share a critical characteristic. None of them currently makes predictions that can be tested with existing or near-future observations. They are mathematically consistent with what we observe. But consistency is not confirmation. A theory that can explain any observation explains none in a decisive sense. The multiverse, the idea that our universe is one of an enormous or infinite number of universes generated by eternal inflation, occupies a similar position. It is a logical extension of some inflationary models. It may be true, but it lies beyond the particle horizon, the boundary defined by how far light has traveled since the hot early state, approximately 46.5 billion light-years in all directions. And by definition, nothing beyond that horizon can send us information, not because the technology is insufficient, because the causal structure of space-time prevents it. The particle horizon is not a philosophical limit. It is a physical one. It is built into the geometry of the universe by the finite speed of light and the finite age of the observable cosmos. Beyond it, we have no empirical access. What lies there, whether more of the same or something radically different, is not something physics can currently constrain. This is worth sitting with. The universe, as we can observe it, is approximately 93 billion light-years across. Our best estimate of the diameter of the observable sphere, accounting for the expansion that has occurred since light from its edges was emitted. Beyond that sphere, the universe continues almost certainly, but we cannot see it, cannot measure it, cannot constrain its properties from within our observational boundary. We are, in a precise sense, islanded. The island is vast and rich and measurable, but it has shores. Return now to the number. 13.8 billion years. What is it exactly, in the clearest terms we can give it? It is the duration, calculated within the ΛCDM framework, between the earliest moment that framework can describe and the present moment. It is derived by integrating the Friedmann equations backward from a universe with the composition measured by the Planck satellite. Approximately 5% ordinary matter, 26% dark matter, 69% dark energy, with a Hubble constant of approximately 67 kilometers per second per megaparsec in the early universe measurement, to the point where those equations can no longer be trusted. It is consistent with the ages of globular clusters, independently estimated at 12 to 13 billion years. It is consistent with the expansion history inferred from supernovae. It is consistent with the acoustic scale in the large-scale distribution of galaxies. These independent lines of evidence all point to the same narrow range. But it is derived. It is not read off a clock that has been running since the beginning. It depends on the model. It depends on the composition values fed into the equations. And there is a tension, the Hubble tension, that suggests those values may not be entirely self-consistent across different measurement methods. If that tension resolves by modifying the model, the age will shift, not dramatically. The evidence constrains it tightly, but it will shift. The number is our best current answer. It reflects decades of increasingly precise measurement, the work of generations of scientists, the development of instruments that can map the sky with sub-millikelvin precision. It is extraordinary that human beings can arrive at such a number at all, that the universe has left enough of a record in light and in the abundance of elements and in the geometry of space for us to read its age within a margin of 100 million years. The number deserves both trust and lightness. Trust because the evidence behind it is real and robust and multiply confirmed. Lightness because it rests on a framework that is effective but incomplete, because the tension in its underlying parameter is unresolved, and because the history of cosmology is a history of numbers being refined. There is something in that history worth acknowledging. When Hubble measured the expansion rate in 1929, his value for what we now call the Hubble constant was roughly 7 times larger than modern estimates, which would have implied a universe younger than the oldest stars. The contradiction was glaring. It took decades and multiple revisions, as distance measurements improved, to bring the expansion rate down and the implied age up to numbers consistent with what we knew about stellar evolution. The consistency we enjoy today was not available to cosmologists in 1950. It was earned through instrument improvement, theoretical refinement, and the willingness to revise. When Penzias and Wilson detected the CMB in 1965, it confirmed a picture that had been treated skeptically for 2 decades. The universe had been hot. The expansion had a history that could be read. The clock could be set. When the supernova teams announced accelerating expansion in 1998, it required the reintroduction of a cosmological constant that Einstein had added and then removed from his equations, a term he later called his greatest blunder. The universe had the last word. Dark energy, whatever it is real in the sense that the equations describing expansion require it. Each of these moments extended the map. Each moved the boundary of what could be measured. Each also exposed a new limit, a deeper question, a component not yet understood, a tension not yet resolved. The map grows, the edges move, but edges remain. Cosmology is not a story of triumphant completion. It is a story of structured advance, of measurements that hold, of frameworks that work within their domains, and of honest acknowledgement where the frameworks run out. The cosmic microwave background is still passing through you. It has been traveling since the universe was 380,000 years old. It carries, in its patterns of temperature, information about conditions that existed long before any planet formed, long before any star ignited, long before the first hydrogen atom condensed out of plasma. It arrives from all directions at every moment carrying a record. The record is not complete. It ends at recombination. Before that, the universe was opaque. Before inflation. If inflation happened, we have no direct signal. Before the Planck time, physics as we know it does not provide a description. But the record we have is extraordinary. And what we have done with it, the measurements, the equations, the calibrations, the arguments and revisions and convergences, is a genuine achievement, not a final answer, but an answer held with appropriate confidence, earned through the discipline of evidence. 13.8 billion years. The age of a universe we understand in part. A universe built mostly from components we cannot yet identify. A universe that, according to our best equations, began in a state our best equations cannot describe. A universe that offers its own archive to any instrument patient enough to read it, and precise enough to notice when the readings disagree. The number is provisional. The evidence behind it is strong. The limits of that evidence are real and mapped with care. And the next refinement, the next instrument, the next detection, the next theoretical advance will not erase what has been found. It will extend it. That is what science does when it is working. It accumulates, it revises, it holds what holds and loosens what must be loosened, and it keeps pointing instruments at the sky, asking questions that can be answered in the only language that crosses the distance between here and the edge of what we can know. The language of measurement. The universe is approximately 13.8 billion years old. We know this because the light says so, and the light does not lie, though we must always be careful about how we read it.